Hello and welcome everyone to the fourth webinar on synthesizing training data with SynthRock for machine learning applications. My name is Hardeep Jaglan, and this is a series of 5 webinars, out of which the first two were presented by Paul DeGroth, and this one and the last one are presented by me. And the final webinar on 23rd of April on creating and adding new models will be presented by Anuhyuk. So in this webinar, we are going to cover primarily the two main synthetic generation tools available in OpenDetect, Volume Builder and the SynthRock plugin. After having an overview of these two tools, we'll go over a case study where we are going to discuss application of the SynthRock plugin in generating pseudo-well synthetic data set for rock property prediction via two different methods. The first method involves a HitCube trace matching inversion type of work, and the second method uses the pseudo-well synthetic data sets to train various machine learning workflows to predict rock property. So the first volume builder tool in the OpenDetect software allows you to generate 2D and 3D synthetic data sets using a number of workflows which are shown here in these red rectangles. This tool can work with well data, horizons, falls, and geobodies. The second and perhaps more advanced tool we have available in OpenDetect for generating synthetic data sets is the SynthRock plugin, which is currently supporting generation of 1D and 2D synthetic data set and can make use of well log data, horizon data, geological trends, statistics, and rock physics models, among others, to generate 1D or 2D synthetic data. It is worth mentioning here that we are currently working on extending SynthRock's capabilities to 3D. So here is an example of the working of the volume builder tool. In here, what we have done is simply use a number of P impedance or acoustic impedance logs from 4 wells and have interpolated them along a number of horizons to create a acoustic impedance model, which is further used inside OpenDetect's gradient attribute to compute reflectivity and has been convolved with a wavelet to generate a synthetic data. This can be done in both 2D and 3D and can be used to train various machine learning models. Now let's move on to the more comprehensive and sophisticated tool, SynthRock. SynthRock is a modern interactive forward modeling and inversion package that has benefited from many years of experience that DGB has in quantitative interpretation. In fact, we started as a QI service provider company back in 1995 and had our first software GDI, Geology-driven integration, which is now available in a more advanced form of the SynthRock plugin. So the SynthRock plugin basically allows you to investigate various what-if scenarios to predict rock properties and associated uncertainties from the seismic data in a geologically sound manner. So where does the SynthRock software fit in the overall G&G cycle? During the exploration phase, SynthRock's profile module can be used to generate wedge models or perform forward modeling and AVO modeling. And the more advanced stochastic module can be used at a later stage of appraisal and field development when you have more data about the reservoir to perform a sophisticated pseudo-well stochastic modeling, succeeded by HitCube trace matching inversion or machine learning prediction or machine learning inversion to create rock property probability volumes, which can in the end be used to create various static reservoir models. So the SynthRock software has primarily two modules, like I mentioned earlier. The more easy to use profile module, which is based on well logs, or it requires availability of well logs, and the more complex stochastic module. In both modules, we have a number of capabilities, such as creation of pre-stack synthetics. You could also incorporate various rock physics trends or models and perform field replacement. And in the end, you could use the synthetic data as input for Bayesian classification via probability density functions, and for HitCube trace matching inversion, and obviously for training various machine learning models. So as I mentioned earlier, the profile module is a deterministic forward modeling package, which requires or which works with the available well logs and markers, and it allows you to create standard two-dimensional wedge models, forward models of fluid contacts to simulate fluid indicators. You could also create cross sections between one or more wells to simulate geomorphological features like channels and ridges, as well as perform variations of rock property, for example, porosity or lithology, to evaluate their impact on the seismic response. And you could, of course, use all these models and feed them to the machine learning workflows that we are supporting in the OpenDetect software. A newly created feature in the profile module is the support of our HorizonCube and SSIS plugin. As you perhaps already know, HorizonCube is a set of automatically tracked horizons from which you could perform your system tracks interpretation. And these interpretations can be used by means of real well logs or even pseudo-well logs to model rock properties in various system tracts or SSIS intervals. And this is an extremely powerful tool to simulate your stratigraphy uh, and use that synthetic data as input to machine learning training. Now, this tool is currently supporting only creation of 2D models, but we are working on extending this tool to 3D. And in there, we are also going to support fault planes. The second and more complex and advanced module of SynthRock is what we call the stochastic module, which obviously, as the name implies, is used to perform stochastic forward modeling, wherein we create a large number of one-dimensional pseudo-well models that are input for HitCube trace matching inversion for Bayesian classifications, as we could extract probability density functions from those large number of one-dimensional models. And obviously, we could use those models and associated synthetic data as input for training a number of machine learning and deep learning algorithms. So a stochastic module is all about pseudo-well modeling. And here we use all sources of information that we have at our disposal. And we integrate information from drill well data, so the information from logs, stops, drilled cores, and knowledge about the geology, the geological regional framework, information from analogs, from outcrops, into a stratigraphic framework, which is supported by rock physics trends and distributions, and some statistics from them, to generate a stochastic subsurface model, which allows us to create realistically looking large number of one-dimensional pseudo-well models that can be input to a process like HitCube trace matching inversion, where we simply take the synthetic traces from each of the simulated one-dimensional pseudo-well models and match them with a real seismic trace in a match window, which is typically around your reservoir. This is a trace by trace matching process and results in volumes of rock properties such as porosity, lithology, saturation, acoustic, impedance, and associated uncertainties from a direct inversion of seismic data. We support both post-stack, pre-stack, and EEI type of workflows in this case. Now, the main topic of this presentation is to showcase the use of SynthRock for machine learning application or various machine learning prediction workflows that we have built in our machine learning control center. Currently, a direct link from SynthRock to the machine learning control center is still under construction. However, we can already export the rock property models from pseudo-wells and the associated synthetic data in an OpenDetect's project database and use them for machine learning model training. So let's move on to a case study from offshore Norway, where we are going to demonstrate application of the stochastic module of SynthRock software by generating a large number of one-dimensional pseudo-well models stochastically for rock property prediction via a physics-based HitCube trace matching inversion type approach, as well as using them as input for machine learning predictions. So the case study presented here is done in collaboration with the MOL Norway, who are also the main sponsors of our machine learning plugin. The Upper Jurassic Reservoir in question here is supposed to have received sand deposits from a nearby basement high, which has shown a strong evidence of erosion. This geological model is also supported by these RGB maps that suggest that channels are coming from the basement high source towards the basin and depositing some material in there. However, the main problem here is that very few wells have penetrated into this Upper Jurassic Reservoir in this area, and in fact, none of those wells have been drilled in our prospects. So this severe lack of well analogs is the biggest risk in terms of delineating the reservoir presence or quality. So the central question here is there a geophysical method that can help us de-risk our reservoir or our prospect, given the closest sand analog well is on the eastern side of this basement high? So to answer this question, we have come up with this quantitative interpretation workflow, where we are considering a number of tools mentioned here in this box. And obviously, for all these workflows to work, there are two prerequisites, one from the rock physics side and another from the seismic side. So for this presentation, we are not going to go into the details of various seismic gather conditioning steps that we carried out in order to provide a nice decent set of noise-free gathers for the QI work. On the other hand, in terms of the rock physics, we are just going to briefly discuss the fundamental trends that are necessary in order for us to proceed with various QI inversion workflows that we have mentioned in this box. Now, in here, we cannot really perform these so-called model-based acoustic impedance inversion or elastic inversion or simultaneous pre-stack inversion workflows, as we do not really have the well-log data in our prospect to create a nice detailed low-frequency background model, which is necessary for all these workflows to work. However, we still have two tools available in our arsenal, which do not really need real well data to be present within the prospect or even within the seismic cube. They are obviously the HitCube trace matching inversion and machine learning inversion. And why are these two tools useful or applicable in this case? This is simply because we could use our stochastic module to simulate one-dimensional pseudo-well models that can form input to both of these workflows to predict rock property volumes and their associated uncertainties from the conditioned seismic gathers. So we are going to start with the first workflow of HitCube trace matching inversion, and then we'll proceed further into the machine learning inversion or machine learning prediction work. So we begin by first analyzing the overall global rock physics trend that we have seen from nearby wells in the Upper Jurassic reservoir in this area. This rock physics information is still a bit of a long shot because it's acquired from nearby wells, which are far away from the prospects that we are considering here. But this is the best we have in this case. Now here, you see in this acoustic impedance versus VP-Vs ratio crossplot, two nice clouds. The top one in blue corresponds to a shale trend, and a sand trend here below with varying porosity, where with increase in porosity from these greenish to reddish colors, you start seeing decrease in acoustic impedance and increase in VP-Vs ratio. So the most plausible geological model here could be of a tight, relatively tight class 1 type of sand, sandwiched between relatively soft shale layers. However, the acoustic impedance range of these shale layers is highly variable. And therefore, from acoustic impedance alone, we can only hope to separate between very soft shale and the medium to low porosity tight sand. So in order to separate, let's say, less soft shale from less hard and relatively high porosity sand here, we need to look at the VP-Vs ratio as well, as this is where they still have separation. And in order to do this, we need to go into the elastic domain and perform a pre-stack HitCube trace matching inversion. So let's dive deeper into the workflow for stochastic pseudo-well modeling and the subsequent HitCube trace matching inversion. This is the step one of this workflow, which simply involves understanding the rock physics or building a rock physics model wherein you could define elastic property trends, their interdependentness, their ranges, their distributions. For example, how for sand and shales, porosity changes with depth, velocity changes with porosity, and so on. The second step is to create a stratigraphic model or a geological scenario. For example, a simple sand shale model, and define in here the rock property trends and internal relationships and distributions for various lithologies that have been analyzed in the step 1 of rock physics model creation. Once this definition is done, we could simply go ahead and generate a large number of pseudo-well models by perturbing these rock property values from corresponding trends and distributions for this particular scenario. Now, we could simply repeat this step and create many other relevant geological scenarios. For example, sand, shale, sand, shale, sand, shale 5 times, or sand, thin layers of interbedded sand between thin layers of shales, or any other scenario that we could think of. In total, in this study, we created 20,000 pseudo-wells altogether. And in the end, or in step 3 thereafter, we simply create pre-stacked synthetic seismograms from each of those 20,000 pseudo-well models. This is a simple process because the elastic parameters, i.e. P-wave velocity, shear wave velocity, and density have already been defined in the various pseudo-well models that we have created. The final step, number 4, is that of trace matching inversion, where we take as input the 20,000 pseudo-well models and their associated pre-stacked synthetic seismograms, as well as a nicely conditioned pre-stacked seismic gather data set. And this inversion process, as discussed earlier in the beginning of this presentation, simply correlates each pre-stacked synthetic seismogram from every single pseudo-well model with every single real pre-stack gather that we have. So this way we can accept the best correlations at each trace location, and we can simply take into the solution space the corresponding pseudo-wells corresponding to the best correlations, and output all the rock properties that we modeled in there. For example, VP, acoustic impedance, porosity, and other parameters, trace by trace. Now here is a porosity map predicted from this HitCube inversion workflow. And in here you could see that from the source of sand, we do indeed see some high porosity, possibly good quality sand carrying channels that are depositing the sand here in the basin. And this is very much in line with the geological model that has been created earlier. So the next step is to use these stochastically generated pseudo-well synthetic models as input for machine learning inversion or machine learning prediction work. So we have already generated these pseudo-well models, and now we are simply going to use this set of 20,000 pseudo-well models with their associated logs and pre-stacked synthetic traces as a training data set for machine learning algorithms. In fact, we are going to use only 75% of the pseudo-wells and keep aside remaining 25% as blind test for our machine learning training. Um, the objective here is simply to train these machine learning models to recognize relationships between rock property logs and synthetic seismic traces, so that once a machine learning model is trained up to a good quality, it could be applied on available pre-stack seismic gathers to directly predict various rock property volumes such as porosity, acoustic impedance, and VPS ratio. The data here for this inversion or machine learning prediction work was played around a bit in terms of what we stacked. So we experimented by stacking the pre-stack synthetic gathers from the pseudo-wells into 13 versus 5 angle stacks, as well as we tried to incorporate the low frequency trend, or let's say the vertical trend, by not only considering the central sample, but also samples above and below while training the machine learning models. So we tested from one sample above and below to up to 6 samples above and below at the central sample for the machine learning training work. As you can see, we tested a large number of classical machine learning algorithms for this rock property prediction work from the synthetic pseudo-well models. Unfortunately, none of them were convincingly able to directly predict porosity from the seismic. And the first 7 algorithms in this list were still weak regressors, even for predicting acoustic impedance and VPS ratio, as the correlation coefficient of prediction was rather low. However, the rest 5 algorithms did a decent job of predicting the acoustic impedance and VPS ratio properties, as seen by a good correlation coefficient between predicted and measured logs for the blind pseudo-well test of 5,000 pseudo-wells, in fact. We consider the 2 algorithms, random forest and deep neural network or multi-layer Perceptron, as the optimal algorithms here, because the last 3 algorithms, albeit performing similarly, are very resource heavy and subject to overfitting at times, because they involve boosting, which is to sequentially fit a so-called base model one after another to improve the prediction. So here is a quick example of the random forest algorithm, which was discussed by Paul in terms of his theory in one of the earlier webinars. When we used total number of estimators or total number of trees as 200 with 50 as the maximum depth, we were able to train this random forest model on our 15,000 training pseudo-well set within 2 hours to achieve a high correlation coefficient in the range of 0.8 between measured and predicted AI and VPS ratio logs for the blind set, the 25% blind pseudo-well set of 5,000 pseudo-wells. So this is the predicted AI versus measured AI for those 5,000 blind pseudo-wells. And we have a nice correlation of 0.8. For VPS ratio, this is slightly less. So we have applied the trained random forest machine learning model to as free stack gathers stacked into 5 angle stacks. And here are the results. On the right, you see the predicted acoustic impedance map from the machine learning workflow. And on the left, for comparison, is the corresponding HitCube predicted acoustic impedance map, again from the same 5 angle stacks. And we see that both map showcase similar deposition trends and patterns. On the other hand, for VP-waste ratio, the right-hand side machine learning results are perhaps more noisy than the results produced from the HitCube trace matching inversion. Although overall, they are both pointing towards the same depositional patterns. So to summarize, both physics-based HitCube trace matching and the machine learning-based inversion approaches were applied in a challenging Norwegian continental shelf setting, which had a severe lack of well analogs. Both workflows relied upon a large set of simulated pseudo-well models and their associated pre-stacked synthetic seismograms that covered various combination and permutations of possible geological realities in the subsurface. Mhm. Out of a multitude of machine learning algorithms tested here in this study, random forest was found to be the optimum one for predicting acoustic impedance and VPS ratio volumes on the basis of the ease of use, ease of understanding, and the prediction power as measured on the 25% blind set of pseudo-wells. However, none of the machine learning algorithms that we tested were able to directly predict porosity from the pre-stacked seismic in this study. In this regard, the HitCube approach was superior. Finally, both workflows resulted in similar looking volumes of AI and VPS ratio and helped us significantly in order to delineate the expected sand shale system in the Upper Jurassic, especially in the absence of any other information or any other technique at our disposal. Finally, I would like to mention some ongoing developments in this field that we are working upon. So we are testing more deep learning algorithms to relate synthetic pseudo-well rock property volumes generated from SynthRock with the seismic response. Some of these algorithms are, for example, temporal convolutional neural networks or recurrent neural networks such as LSTMs and GRUs. And finally, we want to also do some experimentation with generative adversarial networks, or GANs in short. We are also working on extending the SynthRock synthetic generator capabilities to 3D. So in there, we will be able to incorporate the well data, rock physics trends, regional geological trends, horizons, and faults to create three-dimensional synthetic volumes, which are going to be the ultimate training data set for various machine and deep learning algorithms. We are also already working on an anisotropic multi-azimuth synthetic generator to facilitate fracture modeling in SynthRock in order to predict various fracture properties such as fracture density and fracture orientation or fracture azimuth from multi-azimuth seismic data. And finally, our immediate focus is to finish up this easy-to-use link between the SynthRock plugin and the Machine Learning Control Center. And in the end, a big shout out to the MOL group for sponsoring our machine learning plugin and allowing to publish this study. Thank you very much, everyone, for your attention. Please feel free to ask any questions.